I've written the formula for a Laplace transform of a function of t up here on the board. By definition, this is a definition. You're like, where did that come from? Well, we'll talk about that a little bit later, but it's a definition. So somebody gave it to us and said, this is what we mean by the Laplace transform. And then it turns out it's actually kind of useful, and we'll see that eventually, okay? All right, so it's the improper integral from 0 to infinity. So remember we said our functions had to be defined from 0 to infinity, okay? So it's the improper integral from 0 to infinity of our function times e to the negative st, and we're integrating with respect to t. Now I can see how this is going to become a function of s. For the purposes of this integral, I'm treating s as a constant, but I know when I integrate with respect to t, I'm not going to get any t's in my final answer because I'm ultimately going to be plugging in a finite limit of integration, and of course this is going to become a limit as b goes to infinity, and I'm going to be evaluating that limit. So I won't have any t's in my answer, but I will have some s's. Okay. All right, what I want to do is just do a particular example. Let's suppose I wanted to take the Laplace transform of e to the at, an exponential function where it's just e to a multiple of t. Okay. So this is going to be the integral from 0 to infinity of e to the at times e to the negative st dt. That's the integral from 0 to infinity of e to the a minus s times t dt. Now, this is an improper integral. I evaluate improper integrals by replacing this problematic limit of integration, because I can't plug in infinity to a function. I replace that with a variable and take the limit as that variable approaches infinity. So this is going to be the limit as b goes to infinity of the integral from 0 to b of e to the a minus s times t dt. And yes, you must write that. You cannot just be careless and keep everything in terms of infinity. Perfectly acceptable to have integrals written with an infinity here. That just means it's an improper integral. But once we take our antiderivative, we need to plug in our limits of integration. You can't plug in infinity. You can plug in b, which represents a finite number, and then take the limit as that goes to infinity. Okay, I'm going to do a u sub. So I'm going to let u equal a minus s times t. Okay. That means du would just be a minus s dt. So if this is going to work, I'm going to need to have an a minus s. I can introduce one as long as I counterbalance with the reciprocal on the outside. Now, that's only legal if I haven't just divided by 0. Okay, so this is okay if a does not equal s. Okay. If a equals s, then I've got a problem. Okay. And actually, if a is equal to s, notice this would just be e to the 0t, which is 1. I'd be integrating 1 from 0 to infinity. Well, if I integrate 1 from 0 to infinity, that's like saying, how much area is there in this infinite strip? Well, that would be an infinite amount of area. That would be an integral that diverges. Okay. And we're going to see that we only want to do this when we get an integral that actually converges, because, of course, infinity is not a function of s. Okay. So we are going to have some restrictions on s for this particular Laplace transform. And one of those restrictions we can see right now is that s is not going to be allowed to equal a. Okay, but for all other values, I can evaluate this integral now. So I can say this is going to equal the limit as b goes to infinity of 1 over a minus s times the integral from the u value at 0, which would still actually just be 0, because I'm multiplying 0 by a minus s, to the u value at b would be a minus s times b of e to the u du. So that's going to be 1 over a minus s. For the purposes of this integral, s was just a constant, so this is just a constant. I can factor that out. And then we've got the limit as b goes to infinity of, let's see, I can take an antiderivative, e to the u, evaluated between a minus s times b and 0. All right. So let's see what we get. Okay, I'm just going to copy this. 1 over a minus s times the limit as b goes to 0 of, actually I'll go ahead and plug on in, e to the a minus s times b minus e to the 0, which would just be 1. Okay, so if I look at this, this is going to depend whether I get something, I'm sorry, b is going to infinity here. What I get here is going to depend on whether a minus s is positive or negative. If a minus s is positive, this piece would be going off to infinity and the integral would diverge. So I'm going to just create a little table here where I keep track of a minus s and the behavior of the integral. Now we already saw previously that if a minus s was equal to 0, the integral diverges, and for that reason we're not going to allow a to equal s. If a minus s is bigger than 0, this is e to a positive power. If that's e to a positive power, that's going to be going off to infinity. Minus 1, it's still going to infinity. This is going to diverge. But if a minus s is less than 0, okay, then a minus s times b is a negative multiple of b, or is a negative exponent, because b, remember, is going off to infinity. This is going to be going to, now the exponent is going to negative infinity, so the exponential expression is going to be going to 0. Okay, so this is where we're going to get that it converges. Okay, so that's if a minus s is less than 0, which would of course imply that s is bigger than a. Okay, so I'm just going to say this equals if s is bigger than a, ruling out the two cases where we get a divergent integral. Then this is going to equal 1 over a minus s times 0 minus 1. That's negative 1 over a minus s. And usually we'll just write that as 1 over s minus a. So we have done our first Laplace transform. The Laplace transform of e to the at is 1 over s minus a. Why that's going to be useful? Not immediately clear at this particular moment in time, but that is the Laplace transform of this exponential function. You'll notice when we did this, we put some restrictions on s because we wanted to make sure that we got a convergent improper integral. If my integral diverges, if it goes off to infinity or negative infinity or does not exist, none of those three things is a function of s. I can't say infinity is a function of s or does not exist as a function of s. So I have to, if this is going to make sense, get a convergent integral. In this case, we were able to arrange that by making sure that we restricted s so that the exponential expression that showed up in our limit was e to a negative power, and so that it was going to go to 0 as the size of that power increased. In general, we're only going to apply Laplace transforms to functions that have what we call no more than exponential growth. Okay, so f of t has no more than exponential growth if there is a positive number m, so a number m bigger than 0, and a number k, which is also going to be bigger than 0, so that the absolute value of f of t is going to be less than e to the m times t if t is bigger than or equal to k. Okay. Now, what does that mean? Well, basically, if here's my t-axis, here's some point k. I don't care what happens over here, but once I cross this line, I'm going to have this function e to the mt, and the opposite of that would be negative e to the mt, and my function f of t lies within those bounds. It doesn't go above e to the mt, it doesn't go below negative e to the mt. What that guarantees is that when I'm looking at the integral from 0 to infinity of f of t times e to the negative st dt, eventually t is going to be big enough that this term will dominate. This factor will dominate. This factor is going to 0. That's going to guarantee that my Laplace transform, which is this function of s I'm trying to build out of this improper integral, that this improper integral will converge somewhere, so that I do get a function of s, at least for some values of s. Maybe for all values of s, maybe as in the case that we just did, I need to restrict the values of s to be large enough that this is going to dominate. But if my function f of t has no more than exponential growth, eventually this is going to be big enough that this piece will dominate, and I will get a convergent integral somewhere, so I will get a function of s for at least some values of s.